Hi everyone. Here we have 3 podcasts going over the practice unit exam we took on bonding. I'm hoping that it helps erase any misunderstandings. The first one will go over questions 1 through 6, that's this one, then 7 to 13, and then the last 14 to 18. So let's begin. Here's question 1, and it states, base your answers to question 1 through 3 on your knowledge of chemical bonding and on Lewis dot diagrams of, well, that's supposed to be H2S, CO2, and F2. H2S, let me make it so that we can read it. There it is. H2S is hydrogen sulfide, CO2, carbon dioxide, and F2 is diatomic fluorine. Here's the question. Explain in terms of structure and/or distribution of charge why CO2 is non-polar molecule. What's important to note here, it says in terms of. So you must discuss structure and/or distribution of charge. And what are we talking about? CO2, carbon dioxide. That one right there. I prepared my version of what would be an acceptable answer, and if you said anything similar to this, it would be fine as well. So, what did I write? The entire molecule is symmetrical. Notice I mentioned symmetry. So the entire molecule is symmetrical, therefore canceling out any charges caused by the uneven sharing of electrons in the individual bonds. Now let's focus on that just for a moment, because if you take a look at the bond formed right here between this carbon and that oxygen, it is a polar bond. And for that matter, so is this one, but they're equal and opposite, getting to the next possible answer. The charges are distributed so that they are equal, but opposite. This cancels out the charges for the entire molecule. The next question asks, which atom, when bonded as shown, has the same electron configuration as an atom of argon? Electron configuration of argon. Well, let's take a look at argon. Argon, there it is. Argon has an electron configuration of 288. Let's write that down. Argon is 288. So which of the atoms looks like argon after it bonds? Get this out of the way. Now, which are the ones at play here? We have fluorine from right here, oxygen, carbon, hydrogen, and sulfur. So fluorine, oxygen, carbon, sulfur, and hydrogen. Let's go ahead and discover what their electron configurations are. Here is fluorine. There it is. It's 2,7. Oxygen is 2,6. Sulfur is 2,8,6. And hydrogen, we know from the other side of the periodic table, is 1. So fluorine is 2,7. Oxygen is 2,6. Carbon. Oh, we didn't find carbons yet. There it is. There's carbons. Carbons is 2,4. Sulfur is 2,8,6. And hydrogen is just 1. So again, the question is, let's get this out of the way. Which of these, which atom, when bonded as shown, has the same electron configuration as argon? Well, fluorine, when it combines as F2, it sort of resembles, pick another pen so you can see, it resembles more or less 2,8. Okay, oxygen. When it bonds up here, it is now sharing extra electrons that make it look like 2, 8. Carbon, when it bonds, it shares electrons to resemble 2, 8. Sulfur, when it bonds, it shares electrons to resemble 2, 8, 8. And hydrogen, when it bonds, it shares electrons to resemble 2. So our answer must be here. The atom that now resembles argon is sulfur. Now this next question in the bank of 3 questions reads, explain in terms of electronegativity. Must be stated again, in terms of electronegativity. You cannot ignore those terms. They must be used. So why a CO bond in CO2 is more polar than the CF bond in CF2? Well, let's explore those electronegativities. Those can be found on table S. Make this a little bit larger so we can all see. Now, the electronegativity of oxygen is right here at 3.4. The electronegativity of fluorine is 4.0. And the electronegativity of carbon is 2.6. So, as this stated, oxygen is 3.4, carbon is 2.6, and fluorine is 4.0. Okay, now if you recall, when we look for polarity in a bond, we are looking for the electronegativity difference. Well, if we see the electronegativity between oxygen and carbon, the difference here is 0.8. And if we're looking at a fluorine to fluorine bond, we would have to be comparing fluorine to fluorine 4.0 versus 4.0. The difference would be 0. So in terms of electronegativity, why is a CO bond more polar than a CF bond? Well, let's move this out of the way so I could actually write it for you, because it has to be written. The electronegativity difference in a CO bond is greater than that in a fluorine to fluorine bond. Okay, now this question is similar to a previous one. It reads, when a sodium atom reacts with a chlorine atom to form a compound. Now let's stop right there. What is that compound? What will it look like? Well, we have sodium and chlorine. When they join together, a chlorine would be a +1, chlorine a -1. If you do the crisscross, you would notice that the ratio in the formula would be 1 sodium to 1 chlorine. That's sodium chloride. The question then goes on to read, the electron configuration of the ions forming the compound are the same as those in which noble gas atoms. Well, with this we have to do an inspection similar to the one before. Sodium's electron configuration, to begin with, is 2, you see it right here, 281, while chlorine's is 287. So what would be happening here? 281, that's 281, and this is 2 8, 7. Well, we're getting a transfer of electrons. This one electron would be transferring over to here. And sodium, as a result, would take on an electron configuration of 2, 8, while chlorine takes on an electron configuration of 2, 8, 2, 8, 8. And that's when the electron gets transferred over. Which two atoms does this now resemble? Again, sodium now looks like 2, 8. Chlorine looks like 2, 8, 8. Let's inspect. And noble gases, the only place to look for noble gases is group 18. So we're looking for 2, 8. There it is. 2, 8 is right there. And where's 2, 8, 8? Right here. Neon and argon. Let's see. Are those choices? Neon and argon. The answer for number 4 is 4. Question number 5. Which type of bond is formed between the carbon atom and oxygen atom in a molecule of CH3OH? First thing I do is I inspect. Do I see metals, non-metals? Well, totally examine it. As I inspect, I notice a non-metal, non-metal, and non-metal. In no way, shape, or form can an ionic bond be present unless I have ions being formed. And that cannot happen with nonmetals. Remember, all nonmetals have a high electronegativity, meaning they all want electrons to fill their valence shell. In filling their valence shell, well, they become more stable, but they all want to do it. So the only way to achieve this is by sharing electrons. Now, electrovalent. We did not even discuss the term electrovalent. So now we have to look at covalent. Covalent, is it a polar bond or a nonpolar bond? Now we are looking at oxygen and carbon. Oxygen's electronegativity is, oxygen's electronegativity is 3.4, while carbon's is 2.6. Let's write that down. Oxygen equals 3.4, carbon equals 2.6. For an electronegativity difference of 0.8, this one is a polar bond. To be nonpolar, we're looking for something that is less than 0.4. And as our last question for this recording, please go on to the next recordings if you need the additional questions. This reads, at STP, solid carbon can exist as graphite or as a diamond. These two forms of carbon have the same properties. Ladies and gentlemen, I suggest to you that if they had the same properties, they would be called the same thing. So right off the bat, let's get rid of these two. So next, different properties. They both say different properties and the same crystalline structure or different crystalline structures. For your convenience, I provided these two pictures. This one on the left is diamond, while on the right is graphite. The way the atoms arrange themselves in the structure is different, giving them different properties. In fact, the graphite is arranged in such a way that electrons can end up being located between different, let's call it sheets of carbon. Here's another picture that is showing these sheets, which allows some electron movement. That would be nice to know for the unit exam. Wink, wink. The answer for 6 is 3. Whoop, sorry. 4. Different properties and different crystalline structures.